So folks, we're going to dive into solution concentration calculations. For chapter 9, this will really be the only sort of mathematical part. It's really important though. We're all going to encounter this in the real world. So we'll spend 4 or 5 pages here. Of course, there's a homework assignment. And this week, again, there's a recitation assignment that you're going to do and submit the same way you've been doing the labs. And it's all these kinds of problems. So if you encounter a label that says 0.5% alcohol by volume, this funny looking thing, 12M HCl, sodium fluoride, 0.16% weight per volume is what that means. What they're really saying over here is this. They're saying milliliters of alcohol per milliliter of the solution. Now it gets modified a little bit more, times 100%. This funny looking thing over here is moles of HCl over liters of solution. This here sodium fluoride is grams of sodium fluoride over milliliters of toothpaste, basically, but that's our solution. And that gets modified a little bit. Well, what all of these have in common is solute, 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 solution, solution, solution. So our big picture solution concentration is somehow the amount of solute divided by the amount of solution. Now, there are variations of this, but this is what we mostly see. Amount of solute divided by amount of solution. Now, I'm saying amount. Could be a volume, could be a mass, could be moles, could be any number of things. Which leads us to our sort of common concentration units. So you'll see something called mass percent, or weight percent. Volume percent, mass volume percent. The medical folks love that one. So a mass percent is mass of solute divided by mass of solution. A volume is volume of solute divided by volume of solution. Now notice here I put a little asterisk, meaning it doesn't matter what volume units you use as long as they're the same for the solute and the solvent. Solute and the solution, excuse me. And then we have this wacky one, mass of volume. The solute is in grams, the solution is in milliliters. And every single time, these percentages, percent, it's solute over solution. Now, it's grams over grams, milliliters, grams over milliliters, times 100%, just to convert that ratio into a percentage. All right. Well, to get something to percent, we multiplied by 100. What if I had solute over solution, and instead of percent, somebody said, well, what is it per million? I'm going to multiply it by 1,000,000. So when somebody says parts per million, they mean parts of solute divided by parts of solution. And this can be any units, grams, kilograms, micrograms, moles, no, it can't be moles, divided by the exact same units in the solution. Parts per billion, no surprise. Solute over solution. Percent, multiplied by 100. Per million, multiplied by 1,000,000. Per billion, multiplied by 1,000,000,000. Construction management people, maybe ag people, might see this on a site that has a very dilute, maybe nutrient or like a contaminated site. We'll talk about these very low dilution, very low concentrations. And then we switch gears completely. And this is only for chemists, although I see this a little bit in the medical world. If it's moles of solute, I can put moles of solute per liter of solution, we call that molarity. So moles of solute, liters of solution, molarity. We have this thing called osmolarity, which means we're going to take all the moles of all the solutes. So I'm going to put that's supposed to be sigma, sum the moles of all solutes. Important medically, because sometimes we don't care about the molarity of any one thing. We care about the entire molarity of the solution. So add up all the moles of solute divided by liters of solution. So I would argue it's solute over solution, and all we do is change some units. We can use all of these as conversion factors. And I had about 300 or 400 problems on the next 2 pages, I think. Let's look at this. I've got 4 grams of sodium bromide dissolved in 50 grams of water. It says, what's the total mass of the solution? Notice I don't have solution up there. I have solute and solvent, but I don't have solution. And this is the concentration of the sodium bromide in mass. Well, the mass of the solution is, of course, the solute plus the solvent. 4.0 plus 50.0 equals 54.0 grams. And that is the solution. If I want to know percent mass, well, I'm going to put the solute, 4.0 grams, NaBr, solute over solution, 54.0 grams of solution. To convert it to a percent, I simply multiply by 100%. I think it's 7.4% mass. This one here, 9.6. Now, an alloy is actually a solution, in case you're not familiar with that word. So it says, what mass would contain 36.5 grams of the nickel? Well, that's the solute. And the alloy is the solution. We don't tend to think of that, but that is a solution. It's a solid dissolved in another solid. Well, I'm going to do this. 15.8% equals grams of nickel, grams of alloy, times 100%. Solute over solution. There's the percent. That's the conversion. I've got a couple numbers here. 36.5. And that's what I don't know. How many grams of alloy will contain 36.5 grams of nickel? Solve for x. I'm going to let you do the algebra. 231 grams of the alloy. 231 grams of the solution. ppm, divide solute over solution, multiplied by 1,000,000. So I'm going to do, here's a very tiny amount of sodium fluoride. There's a lot of solution. So I'm just going to start 32 milligrams sodium fluoride over 20 kilograms of solution. So I've got solute over solution. The problem is the units have to be the same. So like, okay, wait, it'd probably be easiest just to convert everything into grams, right? So that's going to get rid of milligrams. We've got kilograms there, grams. That will get rid of kilograms. And then to convert it to ppm, I'm going to have to multiply this times 1,000,000. Well, of course, in chapter 1, we memorized this, right? 1 milligram, 10 to the minus 3 grams. 1 kilogram, 10 to the plus 3 grams. And when I do that math, I get 1.6 ppm. And I'm going through this math fast, frankly, neatly, but fast for a couple of reasons, because you can stop the video, go back, rewatch it. It's also problem 9.10 in your book. The answer's in the back of your book. Now, molarity, I have to remember, okay, molarity, solute over solution. It happens to be moles of solute over liters of solution. But I'm just going to start with this. 50 grams, 160 milliliters of solution. So I'm just going to start with that. 50 grams of vitamin B1 over 160 milliliters of solution. Now, I don't know where I'm going to go with this, but I know that concentrations are always solute over solvent, solute over solvent. For molarity, then, I'm trying to get to moles of B1 per liter of solution. That's what I'm trying to get to. So, I play this game. Let's see, I could go milliliters, liters. And that would get rid of that. And bingo, I've got liters. I don't want grams, I want moles. I might go, well, moles per gram. B1, B1. Grams cancel, and then I have moles per liter. Now again, 10 to the minus 3 and 1. And we've been given the molar mass right there, so that makes our lives a little easier. 337 for 1. I do all this math, and I get 0.927 moles per liter. And we have a shorthand for that. Sometimes we say 0.927, and we kind of just do a capital M. Both are correct. All right, let's look at one more page. Oh my gosh, now we got 2 more pages of this. All right, I enjoyed it, but maybe I was getting a little tedious. Now, I've got a 500 milliliter volumetric flask. It literally looks like this with a line at 500 milliliters. Very precise. I want a 7.5% weight volume solution of acetic acid in water. There's my solvent. There's my solute. So I might say, okay, 7.5% volume equals milliliters of solute, milliliters of solution times 100%. Well, I want 500 milliliters of solution. I don't know how many milliliters of the acetic acid I need. I do the math. See, I got a number calculator here. I do the math. I end up with X equals 38 milliliters of acetic acid. Now, it says, how would you prepare? So here's what I'm going to do. 38 milliliters of the acetic acid into the flask. 2, I'm just going to add water until I get a total volume of the 500 milliliters. ppm, 9.11. What is this? Let's just do the lead. So parts per million, no matter what, it's going to be solute 0.15 milligram of lead per kilogram of solution, which is the drinking water. Now, ppm, I just have to have the units the same. So like, well, milligram, gram, that's probably an easy one. Kilogram, grams. Kilograms would cancel. Milligrams would cancel. I'd have grams of lead over grams of solution. And let's see, one of these, 10 to the minus 3 grams, 1 kilo, 10 to the 3. And then to convert that to ppm, times 10 to the 6 equals. And, well, sort of coincidentally, 0.015 ppm. And sometimes we'll write the solute. Now we got a little bit of a twist here. 100 grams of water. Well, I could do this lots of different ways. One way to do it is say, well, why don't I start off with that 0.015 ppm equals, and I've got all this in mass, so grams of lead, grams of solution times 10 to the 6 to give me ppm. Well, I've got 100 grams of the water, x grams of lead. When I do this math, x equals 1.5 times 10 to the minus 6 grams. Not very much. That stuff's pretty toxic. Let's do one of these. Molarity. So molarity I do have to memorize. Moles of solute, I have to memorize that. And the shorthand is usually molarity equals moles of solute over liters of solution. You just have to remember, oh yes, solute, solution, all that stuff. So I've got the molarity, 0.35 equals x moles over 1, well, let's go with this. But this is supposed to be moles per liter. So I could fix that. 10 to the minus 3 and 1. I just have to solve for that x. Now, that's not the only way to do this problem. I'm going to do it this way and then come back. So let's see, I'm going to multiply both sides, 175, divide by 1, multiply that. X equals 0.0613 moles. Now, I'm not going to do that one. It's the same. Let's do it a different way. What if you said, how many moles? What if we started off over here? Like, how many moles do I need? Well, I've got this 0.35 moles per liter. I just think, oh, well, if I could just multiply by liters, I'd have it. I don't. I've got 175 milliliters. And then I say, oh, well, okay, if I had a milliliter to liter conversion, liters would be gone, milliliters would be gone, and we'd have it. So 10 to the minus 3 and 1. So again, it's like all these math problems, multiple ways to do this. Gee, it turns out that I do this multiplication and I end up with 0.0613 moles. It's magic. All right, one more page of intense calculations. All right, we're in the middle of our concentration calculation marathon, page 9.16. It says, we'd like to know this to mass volume percent. So really we're trying to get to grams of the Ca2 plus per milliliter of solution times 100%. That's what we're trying to get to. So I've got this 8.6 milligram per deciliter. Well, that's solute over solvent, solute over solution, excuse me. It's 9 o'clock, I'm tired now. So I think, well, I don't want deciliters, but I probably can't go deciliters to milliliters. So I'd probably do this. And then I'd probably go this to this. And now I think, oh, okay, I got rid of this weird deciliters, liters. Bingo, that's good. I don't want milligrams there, so I might go, okay, well, milligrams, grams, milligrams will cancel, and I've got grams. And then to turn it into a percent, I've got to multiply whatever I get by 100%. So let's see, deciliter, that's a tenth of a liter, if I'm remembering that correctly, minus 1. Liter is a 10 to the minus 3 milliliter. Milligrams, 10 to the minus 3 times 100%. When I do this, I get a pretty small number, but I get 0.0086% mass volume. If it was a normal semester, we would do millimoles, but it's far from normal. Let's skip it. You can do that problem. It's not that tricky. If you want the answers in the back of the book, let's look at this. 9.9. Molarity. Mass of glucose to prepare, excuse me, this is not molarity, percent mass volume. So I might just go back to the definition and set it up. It works too. You could just say, well, 16% mass volume equals grams of solute, milliliters of solution times 100%. And say, okay, well, I've got 125 right there. 25.0. X grams of solute. Solve for X, 20 grams glucose. Volume of water, same thing. 2% mass volume means I need grams KCl, milliliters of solution times 100%. Got grams, 1.20 X. When I solve for X, X equals 60 milliliters. Now, this gets a little touchy because that's milliliters of solution. So I'm going to add water to this to get to the 60 milliliters. It may not exactly add up. If I already put a gram or so of KCl into a flask, it might take more or strangely enough less or strangely enough more water to get to the 60 milliliters. So we're fudging a little bit here because we're sort of saying water is the solvent, and then we're sort of saying that's the solution. It's okay. Welcome to the real world. All right, now some stoichiometry, some chemistry. Here's my balanced chemical equation. I've got something that says 65 milliliters of 0.12 molarity HCl. That's where this reactant is. And I want to know moles of HCl. Now there's more than one way to get there, but I might start with this. 0.12 moles HCl per liter of solution. I think, okay, well, I need liters of solution. I don't have it. I've got milliliters. And if I said, well, what if I did this? 65 milliliters . 65 milliliters there. It's not a ratio of 65 milliliters to anything, but I think, oh, I do have a ratio of milliliters to liters. Gone, gone, and I get only moles left over. Let's see, 1 milliliter, 10 to the minus 3 liters. I do that math, and I get a small number, 0.0078 moles HCl. Now it says how many moles of calcium carbonate do I need? Oh, 0.0078 moles HCl. Moles of the calcium carbonate, moles HCl would give me moles CaCO3. Well, I look at my balanced chemical equation, 2 to 1. So the answer is 0.0039 moles of calcium carbonate. Okay, that's a super fast walk through a handful of reactions. There's like 27 billion more online. There are examples in your book. You'll get this. Now, the last bit of math, we're going to focus on sort of the concept. We're not going to focus on equations. If you focus on equations, it's an $8 an hour job. It's a possibility of making a lot of mistakes. Now, you can find equations to do this, and I'll bet you $100, I can safely say that from the safety of my office at home, I'll bet you $100 you'll get it wrong a lot. So here's my lovely picture. I want to think about diluting a solution. So I've gone somewhere, bought some solution, poured it in the bottom of a beaker, and what I'm going to do is I'm going to dilute it. Dilute. Really by adding solvent. And most of the time that means adding water. Now, I can get all the math right if I think about one thing. When I dilute this with water, what's going to happen to the volume? When I dilute this with water, what's going to happen to the concentration? So this lovely drawing, so I could think, here is my concentrated, and here is my diluted solution. So what happened to the volume? The volume goes up. If I have two volumes, for concentrated and diluted, I know the diluted volume will always be bigger than the concentrated volume. The concentrated volume will always be lower than the diluted volume. Now, what about concentration? Well, this amazing artwork right here shows me that this is very concentrated and diluted. So what happens to the concentration when you dilute it? The concentration always declines. So the concentration of my diluted is less than the concentration of my initially concentrated solution. So all I have to do is remember that. Initial concentration volume is smaller. The final diluted solution volume is larger. The initial concentration is higher, and my diluted concentration is lower. Now there are dozens of different ways to do this math. Here's a way that I really believe you'll get it right more often than not. You can find other ways to do this, but here's what I'm going to say. The concentration equals the concentration times the ratio of the volumes. Now all you have to do is think about, okay, if this is getting smaller or bigger, to which volume do I put on top? Which volume do I put on the bottom? So let's look at this one. Here is a concentration and a volume and a volume. And it says, what's the new concentration? So I might say, okay, the new concentration equals volume over volume times 5.0 molarity. Now I've got two volume numbers. Which one goes on top? Concentration is going to be lower, right? So whatever this is better be less than 1. So how about 0.100 over 1.5 times that. That gives me a new concentration, 0.33 moles per liter, as we'd expect. Oh yeah, the volume went up from 0.1 to 1.5. The concentration went down from 5 to 0.33. Let's do a couple of examples right out of the book to wrap up this concentration marathon. Okay. There's a concentration, and a volume. So let's see. So this is diluted, and this is concentrated. So I know that my volume, initial volume, has got to be less than 500 milliliters. So we'll say concentration. Let's just throw either of these numbers up here. 16. 16.0 equals some volume times 1.25 molarity. Now you could stop the video and think, okay, wait, what am I going to do with those volumes? This is bigger than this, so this number must be greater than 1, which means my final volume, 500 milliliter, over X milliliter. That initial amount must be smaller. I do the math, and I get 39.1 milliliter. Makes sense. It went from 39 concentrated to 50 diluted. It went from 16 moles per liter down to 1.25 moles per liter. The beauty of this system is when you make mistakes, it turns out we're all human and we do, we immediately recognize it. If I had done this math and I came up with, let's see, I need to start with 8,000 milliliters and dilute it to 500. Right away you go, oh, wait, that can't be right. That doesn't make any sense. I must have got something flipped over. All right, one last problem, and we'll get out of this business. And sometimes it helps to maybe make a table. So why don't I do this? Concentrated, diluted. So it says here, I've got a sample of water that's 5 parts per million. And it's 1.5 liters. And I want to dilute it to 0.010 ppm. That makes sense. My concentration goes down. Oh, my final volume goes up. So I can play around with these numbers however I want, multiply, divide, until I get a number that's bigger than 1.5. Let's do it the way we've been doing it. Let's do like this. Let's just go 0.010 equals, and I know it's some volume over volume, times 5.0 ppm. Now I've got 1.5 liters. This is bigger than that. What goes where? Now you might stop the video and think, okay, wait, what am I going to write where? Well, this is smaller, so this has to be less than 1. So I better put 1.5 liters there and X liters there. When I solve this, I get 75 liters. And that makes sense. You go, oh yeah, volume goes up, concentration goes down. Now you're going to see other ways to do this. That's fine. Okay, now you should be starting on, I think it's 96A, 98A. I'm sorry, I can't remember. It's a set of exercise problems that we would have normally done in recitation. This is such an important fundamental skill that we're going to beat this to death. And so you'll do that and turn that recitation in the same way you've been scanning in your lab reports. But to compensate for that, no quiz this week. So no studying for a quiz, no quiz, just work on that exercise set. All right, folks, stay well and hang in there. We're really almost done. Bye for now.